Howdy, folks. This is a harder static equilibrium problem, excuse me. There's one known, and that is the tension, well, excuse me, three knowns. We know the tension on the left cable of this hanging sign, hanging object, and we know the two angles that each of these cables pull at. Okay, with that information, we're going to find the tension on the right cable, excuse me, and the mass of that hanging object. Okay, so there are two things we don't know here. And anytime we have two unknowns, it means we're going to need two equations to solve this problem. Luckily, we have two equations for these equilibrium cases, and those are our net force statements. Our net force statements in each of two directions. All right, I'm going to start with a separate free body diagram. And I'm going to take some care to make it graphically, what's the word I'm looking for, accurate. Let's say here's T2. T2x looks like that. T2y looks like that. Why did I start with T2? Kind of because I felt like it. Actually, I did it because I know that T2 is going to be the bigger force. We talked about that. You see a steeper string like this, it's doing most of the lifting, right? And here's why. One thing I know for sure is that T1x has to be the same size as T2x. They're the only horizontal components of any force in this situation, and in order for this thing to be in equilibrium, they have to be equal and opposite. All right, and that means, well, now since this T1 pulls at an angle sort of like that, there is a reasonable estimation or representation of the force that it exerts. And then I can draw here's T1y. And then based on those two y components, I can make a good representation of mg. The gravitational force. You can write it as either of those ways. Okay? Okay, so the two things we're looking for are the mass of the sign and the tension on the right cable. So you can start with either of these. And here's what I'll tell you. Since you don't know the mass of the sign, there's no way to know the weight. And since you don't know the tension on the right cable, there's no way to know T2y. So in the y direction right now there are two unknowns. In the x direction, however, there are only two forces, one of which we know everything about. We know everything about T1. All right? So I'm going to write my net force in the x direction statement like that. Which means this has to be true. All right? We can express each x component in terms of the whole force and the angle that it pulls at. You'll notice here there's only one unknown. We know T1, we know theta 1, we know theta 2. So we can isolate T2. T1 cosine theta 1 over cosine theta 2. T2 is T1, what is it, 75? Cosine 35 divided by cosine 65? Sure. Yep. Okay. So 75 cosine 35 divided by cosine 65. So T2 145 newtons. What do you think? Well, now that we know T2 and T1 and all the angles, we can go here and write our net force in the y direction statement. We're looking for the mass. That's why I write this as mg. Right? what we said was gravitational force equals mg. Now this is a subscript. This is gravitational acceleration. All right, F g equals m times g. So let's see. We're looking for the mass. T1y plus T2y equals mg. T1 sine theta 1 plus, whoops, T2 sine theta 2 equals mg. Isolate m, substitute, and solve. T1, 75 newtons, sine of 35 degrees, plus 145 newtons, sine of 65 degrees, divided by 9.8. Well, that's all equal to m. All right, 75 sine 35 plus 145 sine 65 equals, oh, you jerk, aha, divided by 9.8 equals, and I get a mass of, well, let's just call it 18 kilograms. What do you think? Not so bad? Not so bad. One thing to notice, you know, we take a little time to draw a physically reasonably accurate free body diagram, and look what T2 came out to be, right? T1 is supposed to be 75, well, is 75 newtons. And what do you notice about T2? Well, it's, you know, it looks about twice as big, doesn't it? We got an answer that's about twice as big. All right, so more and more we're seeing situations where people come up with answers to things, even making measurements for things, and hopefully we're starting to ask ourselves more and more often, is that reasonable? You know, if we switch these around by accident and get a T2 that's half as big as T1, wait a minute, should that be right? So you have lots of opportunities to take a little bit of care, which can help you in the end figure out if the answer you got is a reasonable answer or not. All right, I encourage you to take advantage of those opportunities. Okay. So, you know, the nice thing about these problems, really any and every force problem we do, is that you're going to start with the same thing. And, well, I should really say you're going to start with the same thing. Is net force always going to be equal to 0? No, we know it's not. But we're always going to start with a net force statement. Okay? So most of us are pretty comfortable with that right now. That's great. Keep practicing if you need to. You got to, for sure, by now, understand why forces are either positive or negative, or why we write them as positive or negative in our net force statements. Right? We use a standard convention that says up is a positive y direction, right is a positive x direction. So you'll notice, for example, that T1y is upward, T2y is upward, mg is downward. Hence, we're really saying that's positive. Notice, positive. Notice, negative. All right, same thing applies over here. T2x is to the right, T1x is to the left. We're really saying positive here. Notice, negative. So sign and direction have to agree. Okay? Okay, folks. There's our 2-equation, 2 unknown, hardest hanging sign you'll ever have. Adios.